Last time in our explainer, we looked at how modern ships use physics to find true north. But let's put that to the absolute ultimate test. Picture a truly terrifying scenario. You are on a 200-meter steel ship. You're 200 miles from the nearest coastline. It's 3 a.m. There's no lighthouse, no landmark, literally just pitch black water in every direction. Suddenly, you suffer a total electrical failure following a major incident. Every single digital screen on the bridge goes completely dark.
Total blackout. Your high-tech gyrocompass? It dies instantly. On a modern integrated bridge system, which is basically the digital brain of the ship, this is absolutely catastrophic. Your autopilot, your radar, your electronic chart display, they all rely on this compass to know which way the ship is facing. Without it, you are left completely blind to your heading in the dark. So now what?
Well, to really understand what we just lost in this power failure, we need a quick refresher on the gyrocompass itself. It's a highly sophisticated instrument that tracks true geographic north, and it's totally independent of the Earth's magnetic field. That true heading data is absolutely critical. It acts as the primary feed for a massive range of bridge equipment, making sure everything is oriented correctly against true north, because that's what your charts and GPS actually reference.
It's honestly fascinating how this device manages to find true north without magnets. Think of the traditional mechanical gyrocompass like a spinning bicycle wheel held fast by its axle. Because of its intense angular momentum, it resists being tipped over. It actively corrects itself through physics, aligning its axis with the Earth's rotation to literally seek out true north. And because it relies purely on physics and rotation, it simply doesn't care about magnetism. It is completely unaffected by the ship's massive steel hull or the electrical fields generated by the cargo and machinery.
Modern ships actually take this even further, replacing those mechanical wheels with fiber optic gyros, or fogs. Instead of a spinning mass, they shoot beams of light in opposite directions through a coiled fiber. By measuring how that light travels as the ship turns, it calculates your heading with zero moving parts, zero maintenance, and total immunity to magnetic interference. I mean, it is a brilliant piece of modern engineering.
But here is the ultimate catch when it comes to maritime engineering. If that primary gyrocompass needs electricity to shoot those beams of light or spin that rotor, we absolutely need a foolproof failsafe. And this brings us right back to the magnetic compass. It's arguably the oldest and simplest instrument on the ship. SOLAS regulations, the international laws governing safety at sea, mandate its presence precisely because it requires zero electrical power. Ever. It is kept completely disconnected from the digital hub for a very good reason.
But wait. There's a massive, inherent flaw with the magnetic compass, right? It gets heavily thrown off by the ship itself. Remember, sailing ships used to be made of wood. Today's ships are basically giant floating magnets. So how can we possibly trust a magnetic needle, completely surrounded by thousands of tons of steel?
The interference is not just a minor glitch either, it is significant. Depending on the vessel's heading, a loaded tanker's massive steel hull and machinery can easily throw a magnetic compass off by 5 to 10 degrees. That is a huge discrepancy when you're trying to navigate blind in open water without your digital charts.
Let's translate that error into real-world danger. If you rely purely on an uncorrected magnetic compass for just a 20-mile transit, that 5 to 10 degree error equates to being pushed over a full mile off your intended track. In narrow channels or hazard-filled waters, 1 mile off track is the difference between a routine voyage and a devastating grounding.
This is exactly why professional mariners carry a sort of cheat sheet known as a deviation card. Because magnetic north and true north aren't the same, and because the ship itself creates magnetic errors, certified technicians regularly calibrate the compass and create this card. It manually documents exactly how much the ship's structure throws off the reading at every specific heading. You absolutely must know how to read and apply this deviation card before the emergency happens, because when the lights go out, it's the only way to correct your manual heading.
Think of the ship's modern integrated bridge system exactly like a cutting-edge smart home hub, where all your lights, locks, and appliances are connected. It's incredibly efficient, right up until the Wi-Fi or power goes down. The magnetic compass is exactly like a battery-powered flashlight you keep in your kitchen drawer, specifically because it doesn't depend on that same vulnerable grid. True redundancy requires genuine independence, not just a backup power supply for the same network.
So I want you to ask yourself, keeping everything we just covered in mind, in that terrifying scenario, a total engine room fire resulting in a complete electrical blackout at 3 a.m., which heading reference still works to save the ship and guide the crew?
The answer, of course, is the magnetic compass. This proves exactly why redundant heading systems are a deliberate and vital design philosophy on every single bridge. You have your primary, highly accurate gyrocompass finding true north through physics, and your independent, entirely analog magnetic compass. They complement each other perfectly because they fail completely differently.
Thanks to these incredible systems, your ship now knows its precise position and it knows its exact heading, even in the absolute dark of a total blackout. But there's one final piece to the puzzle. You know your heading, but what happens when you don't know what obstacles, storms, or other massive vessels are lurking right in front of you in the dark? Next time in The Explainer, we tackle collision avoidance and marine radar. Until then, how safe would you feel navigating completely blind? See you next time.